Hello. I thought a video would be easier. So you've asked why we travel faster at the equator than at the poles. I'll see if I can answer that for you. Let me start by pulling out some formulas that we'll use. So this is just geometry. If I have a circle, I've got some radius r there, and I want to know some arc length. I'm just going to call it s. And I know the arc length s, this distance, is going to be equal to the radius times the angle. This angle, as I'm using, is going to be in radians. And remember that there are 2 pi radians in a circle. So if I go a full 2 pi here, then that's going to give me the circumference, which is 2 pi r. And that's the circumference of a circle, we know that. I'm going to be using this little bit of an arc length. And then physics, let's just call, just so we have our definitions down, velocity is going to be the distance you travel divided by a given amount of time. Velocity is distance over time. Okay. So I'm going to use that puppy. And let's start our derivation. So let me draw a beautiful sphere for you. Beautiful. Oh, yeah. There we go. Look at that. Spheres are my favorite to draw. Look at that. Look at that. So there's my sphere. This is my Earth. I've got an axis running through, the rotational axis, right here. Now let's look at the equator here. And I'm going to take a slice here as well. It's very close to the pole. I would draw the pole, but it's going to be too small to see. So instead, I'll just take this little section here above it. Dook, 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 dook. And there we go. So let me pull this guy out. And I'm just going to take this and make it 2D, the same as above. So let me take this and turn it on its side so you can see that slice. All I'll do is take a slice out of it. I hope you can see that. There you go. And I'm going to take this one and let me show you the slice. And I try to draw it proportionally bigger so you can see that. Okay? So this guy up here, here's my axis. The axis, center point. Let's say this guy has a radius of, I'll just call it R1. And let's say this guy has an axis of R2. Okay? If I look at the change in angle with respect to time, if I look at its rotational speed, how fast is it spinning, then what I want to see is the change in theta. So is that theta? And here's the theta. I want to see the change in theta with respect to time. So that's going to be the change in theta 1 with respect to time for this guy up here. And then I've got this change in theta 2 with respect to time down here. But I'm going to say that these two things are equal because it's just a more or less solid object rotating. It's going to rotate at the same speed. So, sorry, it's the same angular speed. So I'm going to define this quantity as omega, angular speed. Different than velocity, angular speed. It's just how fast it's rotating. But that's not velocity itself. That's just angular speed. That's how fast is the angle changing over time. So let's look at velocity. To do velocity, I want to know a distance over time. So I'm going to take this arc length up here. I'm going to call it S1. That's the distance that you're traveling. If you're a little person standing here, whee, or a little person up here, whee, then you'd be standing here. I can't draw it there. Or you'd be standing here. There you go. So there you are, whee, and you're traveling around this arc length. I'm going to call this one S2. So if you're on S1, velocity equals the distance over time. The distance in this case is going to be S1 over time. I'm going to call it V1. And for v2, distance over time, I'm going to call it s2. Okay? But what is s1? S1, as we've seen in our formula here, is r theta. So r1, and the theta we said is the same, right? So it's r1 theta, and that's over time. And this is going to be r2 theta over time. But what is theta over t? We just defined that here. Theta over t for both is the same, that's omega. So this becomes r1 omega, and this becomes r2 omega. So I'll just rewrite them here so you can see it. v1 equals r1 omega, and v2 equals r2 omega. We see that the actual speed that you're going is proportional to the radius that you're at. So let's sanity check ourselves. What this is saying is, if the rotational speed is constant, which it is for something like the Earth or a ball, then it's saying you have to, if I take this S and I unroll it, I'm just going to unroll it and make a line out of it. And I'm going to take this S. I'm just going to unroll it and make a line out of it. It's saying that if you're running on both of these lines and you have the same amount of time to cross both of them, you have to be running faster on this line than you do on this one if you're going to complete them in the same amount of time. So if you have a second to go here and you have a second to go here, you'd have to be running twice as fast, or some number as fast, to go on this one. And that's what it's saying.